Hello everyone, this is Jack Hansamon. Today I'll be talking about measuring physiological work. In this lecture, we will talk about another way to measure work. We want to measure work difficulty by assigning some numbers to it. These numbers are based on some physiology concept, and some will be based on the risk of musculoskeletal disorders, which we call ergonomic score. From our previous lecture, we focused on measuring time to perform the task. We have not talked about measuring work difficulty, which is also very important when we design jobs for our human operator. This can be done by measuring force, energy, fatigue, heart rate, etc. on the operator during the work. Human body uses muscles and bones to perform work, especially skeletal muscles. Muscles are made up of muscle fibers bound together by tissue. These muscle fibers contract or expand when we use our muscle to perform a task. When we do not use our muscle fibers are said to be at resting length. According to physiology, humans can achieve maximum muscle strength by having muscles at mid-range of resting length and at zero velocity or static contraction. Thus, a task requiring considerable muscle force should be performed at this optimum position. The higher the speed of the task, the less muscle force we can use. Work tasks should be designed to take advantage of this knowledge. We should look at overall body posture when performing a task, which muscle or joint motion are being used, and which direction our muscle fibers apply the force on, lifting, pushing, or pulling. There are many extensive studies to measure human strength for both men and women. Here are just some examples. We can look at these tables to get some ideas about how much force our male and female worker can undertake for a given posture or task. There are four specific tools that we will cover in this lecture. First is muscle endurance limit. There is a relationship between endurance time T and required force F as shown in the equation. This can be presented as a graph on the left. The dashed line is at roughly 17.5% on x-axis. This means if a worker uses below 17.5% of his maximum strength, his endurance time limit is infinity. He won't get fatigued by the work. On the other hand, if the worker uses about 50% of his maximum strength to perform the work, after about 1.09 minutes of continuous work, he will start to get fatigued. The second tool is energy expenditure. Workers should warm up and start heavy work slowly to avoid fatigue and burnout too quickly. We can estimate energy used in performing a task by measuring air volume inhaled and exhaled. This equation calculates power or energy expenditure in kilocalorie per minute. It is based on an estimate that for every 1 liter of oxygen inhaled, our metabolism will generate 4.9 kilocalorie. So we measure volume of air inhaled V by a special equipment. Typical air inhaled has about 21% oxygen, while the air exhaled has about 16 to 18% of oxygen. This is how we measure energy expended while performing a task. Every activity that we do, including sitting still, will have energy expenditure associated with it. Pictures here show some examples of energy expenditures associated with activities. Generally, there are limits on energy expenditure that our worker should be able to maintain within 8-hour work. For men, about 5.33 kilocalorie per minute is the maximum allowable. For women, about 4 kilocalorie per minute is the maximum allowable. If an operator works beyond this limit, he will need some recovery time during the working time. This energy expenditure estimate and its limit can be used to calculate work-rest cycle. The ratio of rest time to total work time R can be calculated by this equation. So let's say if a male worker needs to perform a task that requires 9.33 kilocalorie per minute, R will be 0.5, meaning that our worker should work 50% of total working time. For example, he may work 1 hour, then rest 1 hour, then work another hour, and so on. Also, we should note that 5.33 in the formula is a limit for male worker. If we consider a female worker, this 5.33 will be replaced by 4. The third tool is heart rate guideline. It is probably the easiest tool to measure work difficulty. We simply measure operators' heart rate before, during, and after work. Obviously, heart rate depends on operators' health, and it varies a lot from one day to another. The guideline is quite straightforward. The difference between average heart rate during work and pre-work heart rate should be within 40 beats per minute. If this is not true, work may be too harsh for our worker. We also measure heart rate 2 times after work. 0.5 to 1 minutes after work, heart rate should be less than 110 beats per minute. 2.5 to 3 minutes after work, heart rate should drop from the previous reading by at least 20 beats per minute. If any of these conditions is not true, again, work may be too harsh for our worker. The fourth tool we will discuss is ergonomic score. There are two main approaches here: to evaluate workers' posture or to evaluate a lifting task. In this lecture, we will focus on evaluating workers' posture using a tool called REBAR. REBAR is short for Rapid Entire Body Assessment. It was developed to rapidly evaluate risk of musculoskeletal disorders (MSD) associated with certain job tasks. REBAR is to assess employees' worst-case posture at one point in time. So we need to follow our worker around a couple of days to select his worst posture. We need to select either left side or right side of the body to evaluate. Usually it is obvious which arm is in the worst posture, so we can pick that arm to evaluate. We should note that REBAR does not consider the duration of the task, available recovery time, and hand-arm vibration risk. To illustrate this, I use REBAR template and example from website Ergonomics Plus. The template here contains 13 steps to determine REBAR score along with all necessary information. The best way is to show how to determine REBAR score in 13 steps from example. Let us say we have selected the worst case posture from our worker, as shown in the picture here. She's trying to assemble something in the black tank. Step 1. Locate neck position to get neck score. Here her neck bends very little, probably within 20 degrees. So neck score is 1. Since her neck is neither twisted nor side bending, so no need to adjust neck score. Step 2. Locate trunk position. We can see our subject bends forward, but probably within 20 degrees, so trunk score is 2. She does not twist her body, but seems to lean her body to the left. With this side bending, we need to adjust our trunk score by 1, so the trunk score is 3 now. Step 3. Consider leg position. From the picture, her legs look rather straight, so the leg score is 1. Since she does not appear to bend her knees, no additional score is added. Based on neck, trunk, and leg score, we can use Table A in the worksheet template to determine posture score A. So step 4, we have posture score A equals 2. Step 5, we need to estimate the load that her right hand is dealing with. It doesn't appear to be heavy, probably between 11 to 22 pounds, so we use load score equals 1. Step 6, we combine posture score A and load score to get score A equals 3, which will be used later in Table C, but we need to consider her arm and wrist to determine score B. Step 7, we locate upper arm position with respect to the trunk. It appears her right arm is raised slightly more than 90 degrees from the trunk, so upper arm score starts at 4. Then we look at adjustment. Her right shoulder is raised higher than the left, so we add 1 to the upper arm score. And her upper arm is stretched or abducted, so we add 1 more to get upper arm score 6. Step 8. We locate lower arm position with respect to upper arm. If the lower arm is in natural position, the lower arm score will be 1. Here, her lower arm is not in natural position, so the lower arm score is 2. Step 9. We locate wrist position. Even though we cannot see it in this picture, we think her right hand is bent a lot. That will give wrist score of 2 as a start. Since her right hand should be twisted also while working, we add another one to give wrist score 3. Based on upper arm score, lower arm score, and wrist score, we can look up posture score B from table B in the worksheet. Here we have posture score B equals 9. In step 11, we add coupling score by evaluating how our subject used her hand. Even though we could not see her right hand clearly, we think she's carrying or gripping something in fair position. Not the easiest, but not awkward either. So the coupling score is 1. Adding it to posture score B gives score B equals 10. With score A equals 3, score B equals 10, we locate table C score to be 8. Step 13. We evaluate overall activity of our subject starting at score 0. If she has one or more body parts held for longer than 1 minute, we add 1 to activity score. If she has repeated small range of actions, usually more than 4 times per minute, we add another 1 to activity score. If she has rapid change in posture or unstable base, we add 1 again to activity score. From our picture, this falls in case 2. We only add 1 to our original activity score to make it 1. Table C score plus activity score gives us finally rebar score of 9. Based on the recommendation, rebar score 9 has high risk for long-term musculoskeletal disease, so we should investigate and change her posture. One way of doing this is to flip the black tank so that our subject uses her arm in horizontal direction. With the same evaluation, rebar score decreases from 9 to 4. So, as you can see, we learn a lot in this lecture. If you have any questions regarding this lecture, you can ask me in our Google Classroom. Okay, I'll be happy to answer. Thank you and have a good day. Bye.